Okay, so let's continue with the last session of the morning. This is going to be by Stephen Wilson, and he's going to continue with some case studies of Kagome metals.
Great, thank you. Thank you very much. Thanks for the introduction, and yeah, the coffee break, I spilled coffee all over myself just in time to give my talk, so this is great. So for the second lecture, what I want to do is I want to try and build on some of the concepts that I introduced in the first lecture, and by trying to illustrate whether or not some of the ideas can actually be realized or manifest in real materials. And to do that, I guess I'm just going to try and bombard you with some series of case studies that maybe some will interest you, maybe some won't. And somewhat of this will be, it's not an exhaustive review of all of the material case studies of Kagome lattices in literature, but it'll hopefully highlight some of the avenues that people are pursuing currently. Good. And so just as an outline, I'm just going to try and walk through case studies in sort of 4 different regimes. And so like the first will be some materials where people believe that this sort of flat band can be seen that's predicted in the Kagome lattice. And in some examples that if the flat band can be tuned towards the Fermi level, that's indeed enhanced correlation effects seem to manifest. And then the sort of second class is I'll be talking about maybe more trivially just systems where there's a large anomalous Hall effect that's observed due to sort of gapped Dirac points in the due to the Kagome band structure and the strong Berry curvature associated with that. And then the third class is I'll be talking about systems where the filling is near the Van Hove filling, okay, and the symmetry breaking that occurs in some examples of materials. In that class of materials, in particular, a series of charge density wave superconductors, but also looking at some other examples where there's some interesting sort of, I guess some people call it crystal frustration, but more or steric frustration in the lattice due to a lattice instability that's not directly associated with the Kagome lattice, but indirectly couples through the Kagome lattice. And then the final bit, if there's time, I'll just say there's some other maybe avenues that can be pursued and other interesting facets in other Kagome systems. Okay, so first just, again, repetition is the mother of all learning. These are the 3 classes that we're going to be looking at, right? So a third filling near the Dirac point, near these saddle points, which are the 3/12 and 5/12 filling, and the flat band filling, okay? And just as a review again of what I ended the last lecture on, is there's this very nice work by Leslie Shoup's group where, again, one can think kind of qualitatively when thinking about real materials of a tolerance factor looking at the, when you define a Kagome net, looking at the distance within the Kagome net relative to bonding with other atoms outside of the net to try and understand, how Kagome is this material, okay? So finding a Kagome network, but then how isolated will it be in the lattice and how much will it contribute to the band structure such that you can have, regimes where maybe there's Kagome bands which are expected to be at the Fermi level to the opposite extreme where you basically have a 3-dimensional network which is doesn't map directly in anything you would expect directly from the Kagome network. And so, in this paradigm, right, these 2 I already mentioned, but, ideally one wants a chemically 2D material, okay, as much as possible. And a lot of these systems that I'll be showing you in terms of materials case studies are not chemically 2D. Some are. And then the other thing is when we go through some of these, just be mindful that there's multiple orbitals in these systems, okay? And in some cases, there's multiple Kagome sites, so this makes the band structures very complicated. So it requires a little bit of like a lover's eye when you're looking at the band structure to try and tease out features that one might associate with a Kagome band structure, okay? So be a little patient with that. Okay, so to walk through a few examples that have been studied in recent literature looking at Kagome metals, either near flatband fillings or first just observing flatband fillings, okay? And so again, the flatband is coming from this compact localized state naively, which is due to quantum interference effect, and this gives you this flat band, which people like because you have this sort of localized state that's highly susceptible to interaction effects. And so here's one example. So this is iron tin. And if I'm drawing the Kagome lattice on this, just doing the nearest neighbor distance, here's the iron tin lattice. This is sort of a nice prototypical structure to start from. And if you look at sort of the DFT of this system, you can see here's the Dirac crossing at the K point. And there's sort of a flattish band, which is down here and then down here. But other than that, you can see that the system is actually quite three-dimensional. So you can see there's a lot of dispersion due to further range hopping. But this system also is magnetically ordered. So it's an antiferromagnet. And one of the oddities of this system is that when it was studied, this is by Ricardo Komen's group, when you look at angle resolve photoemission, which I think Ming is going to talk about the technique, but for those of you who are familiar with it, it's just a way of experimentally probing the band structure in a momentum resolved way. There's this odd flat band near the Fermi level, which isn't really captured in the DFT. And I think this flat band at the Fermi level is coming from actually a surface Kagome band, which is due to like the Kagome termination. Okay, and so this is just to highlight that even the bulk DFT may not be capturing potentially useful surface bands that are still related to the Kagome lattice, and people have interest in maybe using this for devices, for instance, trying to access the Berry curvature associated with that band. Okay, so this is one example. Okay, but one that does have a bulk flat band that seems to be reasonably close to the Fermi level is the same structure. This is now cobalt tin. So this is a non-magnetic Kagome lattice. And again, it's the same structure. So you have this now, in this case, it's a Kagome net of cobalt ions. And so here's the DFT band structure. And so there's sort of if you look in this AHL line, you can have a flat band that then disperses along KZ, and then if you look in sort of the MK gamma plane here, you can see there's sort of a dispersive flat band, but this is sort of what's identified as the flattish band in this material, which has some dispersion, likely due to next nearest neighbor hopping and extended hopping effects. Okay, so this is what qualifies for a flattish band in a Kagome system in a three-dimensional material. And okay, so what's interesting is that one can actually see this, right? This flat band with photo emission results. So this is, again, results from Ricardo Komen's group. And it's below the Fermi level, okay? And so, but this system is chemically tunable. And so there's some very nice work. This is from Brian Sales. And so you can actually then basically chemically dope this system. So you can alloy the tin side with indium, okay, and try and sweep the Fermi level down so the flat band reaches the Fermi level. And as you do so, you can see you start to increase the density of states at the Fermi level. And if you look at sort of, this is a heat capacity divided by temperature as a function of T squared. So these are Sommerfeld fits. So you can extract the Sommerfeld coefficient, which is really the intercept here on the y-axis, as a function of doping. So you can see as you go from the undoped system where this flat band is below the Fermi level to the doped variance, as you're sweeping the Fermi level down towards the flat band, you can see the density of states is going up at the Fermi level via the increase in the Sommerfeld coefficient, which, okay, they've plotted here. And then at a critical level, at around 35%, basically antiferromagnetic order forms. So basically, as you kind of use this flat band to kind of sweep to the Fermi level, one can induce magnetic order and correlation effects. Okay, so this is just an example of some stuff that's been studied in terms of tuning flat bands. And this is a chemically tuned system. Another example is a recent example is by nickel-3 indium. Okay, so this is a more transition metal-rich version of the same structure. Okay, but now if you plot the connectivity of this lattice, you can start to see it's more three-dimensional. But because of the orbital content of this particular system, it still remains somewhat fairly Kagome-like. Okay, meaning the orbitals are kind of within the plane. And in this case, this is some work by Joe Czekowski's group. You can see here that there's a flat band that's predicted by DFT to be actually sort of at the Fermi level, okay? And this is natively at the Fermi level, so there's no disorder that is required to be introduced to like basically alloy the system or anything like that. Okay, and so that's interesting. And so then, and actually in response, basically, if you look at things like, for instance, the heat capacity now is a function of temperature, and you look at this sort of Sommerfeld term, you see an enhanced Sommerfeld term in this, and you see signatures of strong correlations by looking at, for instance, you could do this sort of this Katawaki-Woods ratio, looking at the A coefficient in terms of from transport, as well as the as a function of the Sommerfeld coefficient. You can see it sits up here on this line with some other sort of more strongly correlated transition metal compounds. And then the other thing you can do is you could say, okay, let's take a look at this compound and just replace indium with tin, and in doing so, when in principle moves the Fermi level up away from this flat band, and then you can see there's a dramatic reduction in sort of the Sommerfeld term. So this is, I guess, sort of one of the more state-of-the-art systems that seems to have a flat band that's near the Fermi level, and so there's more kind of lots of work going on trying to tune this particular material, but also looking for other instances where this happens natively. But it just sort of gives you a flavor of some of the Kagome systems in the literature where the flat band is of interest. Okay, that's an example. So the next example is we can just look at effects from Kagome metals due to the gapping of the Dirac points, which, as I mentioned earlier, the gap points can get, the Dirac point can get gapped via spin-orbit coupling, or you can have magnetic order in the system. And in principle, in an ideal case, you could form a strong topological insulator if you're sort of in the gap. But in general, these are multi-band systems in real materials. People, in general, are just looking for like strong anomalous Hall effects that are associated with this gap Dirac point. Okay. So here's an example. This is iron 3 tin 2. So this is kind of a stacked variant of iron tin. Okay. And you can see it's somewhat, in terms of the connectivity, you have Kagome planes that are sort of coupled into bilayers. So now you have multiple Kagome planes per unit cell. You have multiple orbitals per unit cell. And this sort of bilayer structure, you can see, this is now getting very complicated in terms of band structure. But if you look at the K point, you can start to see from DFT, in this sort of spin polarized band structure, there's sort of gapped Dirac points. And this system is a ferromagnet. Okay. And it's a system that has a large anomalous Hall effect, and this gap Dirac points can actually be visualized directly via ARPES. This is via, I guess, also work by Ricardo Komen's group. And the large anomalous Hall effect, due to this out-of-plane ferromagnetic order, has been fairly well studied and identified for quite some time now. So it's I think it's like maybe 2 orders of magnitude larger than iron, for instance. Okay, so it's a strongly enhanced anomalous Hall effect. So that's an example. So another example. This is now a different structure type. So this is moving away from these 1-1 systems where you're kind of adding, you're changing the mix between the iron and the tin, for instance. Now this is a ternary variant, so we've added a third element into the mix, and this gives you the so-called 1-6-6 structure. Okay, so this structure. If you're looking in sort of the literature of Kagome systems, there's a lot of work in these structures. There's a lot of these materials that stabilize in this particular structure type. Okay, and so one way to think about this structure is you can start with the iron-tin structure that I showed you earlier, and you can say, well, when I look at the planes of this system, right, there's a Kagome lattice. In this case, it's labeled as vanadium. You can envision it as iron or some other transition metal. That's fine. In the center of the hexagons of the Kagome plane, I have a tin atom, okay? But in the interstitial layer here, I also have a second tin site, and this forms a honeycomb lattice, okay, in this plane. And so you can imagine there's sort of a void in that honeycomb lattice where I can maybe put another ion, okay? And so let's say I put a lanthanide ion in that space, okay? And so what that does is sterically, it's going to just push this tin atom up, and then the one below it down, okay? Because I'm kind of like, I'm filling the void here in this hexagon, but there's there's an interaction between the rare earth site and the tins above and below. Okay, and so basically what that allows you to do is then I can only insert these rare earth ions into every other layer. So then that gives me this structure here, which is this bilayer Kagome lattice structure, and this is the so-called 1-6-6 structure. It's some way to think about it. It's basically a derivative of the iron-tin structure, but adding in these lanthanide moments. And I'll come back to this in a second, because one interesting degree of freedom that affords you is that you can tune the magnetism on this lanthanide site, and you can tune it and realize many different types of magnetic states that in principle are sort of natively interfaced with the Kagome planes. Okay, but in this particular case, terbium manganese 6-tin-6, the manganese site itself is magnetic, and the terbium basically has induced order via the manganese mean field. And so what it does is it's basically a ferrimagnet, and it's with a net ferromagnetism out of plane. And the system also realizes a very large anomalous Hall effect. It has strongly uniaxial magnetism, and there's, again, due to Dirac points that have been gapped, as seen via photoemission and scanning tunneling microscopy. In this case, this is via quasi-particle interference. Okay. Good, okay. So that's sort of some instances where people are realizing large anomalous Hall effects due to ferromagnetism in Kagome metals and sort of the physics associated with gapping the Dirac points in those systems. Okay, so next I want to talk about is Kagome systems which are near the Van Hove filling, okay? And it just as a reminder, so for Kagome systems near the Van Hove filling, the idea is that you have sort of these kind of near singular density of states that can be nested across the Fermi surface that can create peaks in the real and imaginary part of the sort of Linhard susceptibility, and one can induce electronic instabilities, things like charge density wave order, or in some regimes, superconductivity. Okay, so one system that this sort of in principle embodies this physics is this ternary compound. So it's an alkali metal, 3 vanadium ions, and 5 antimony ions. So people call this 1, 3, 5. Okay, and so the structure here is such that the Kagome net is formed by the vanadium ions, and each vanadium ion sits in the center of an octahedron of antimony. So you have these V3sp5 blocks, and then these guys are spaced in a layered structure by these alkali metal ions, okay? And so there's 3 alkali metal ions that can form this structure. There's potassium, rubidium, or cesium, okay? So if I look down the c-axis of this structure, here's the Kagome structure, which is formed via the vanadium ions. Okay, if you look at the band structure of these 3 compounds, to a qualitative approximation, they're nearly identical, okay? And the key features are the majority of the density of states at the Fermi level are comprised of the vanadium d states, which is what you want if you want the Kagome physics to be important in this system, with the exception of one band here, which is this electron-like pocket here. This is forming from the antimony pz orbitals in the Kagome plane. But, okay, if you look at the K point in the system, you can see here's the Dirac crossing. But then if you look near the Fermi level, there's a series of 3, so 1, 2, and then there's one up here, Van Hove points, which are due to these saddle points in the band structure, associated with different orbitals in the Kagome plane. Okay, and they're fairly close, or predicted to be fairly close via DFT to the Fermi level, and so the idea is that perhaps these can induce some instabilities. And these systems indeed do show forms of electronic order, so they're charge density wave superconductors. Here I'm just showing you plots of each compound, right? So this one is the cesium, this is potassium, and this is rubidium. And this is just, for instance, susceptibility or resistivity as a function of temperature, showing at a low temperature these systems become superconductors. And then at higher temperatures, roughly at near 100 Kelvin, all 3 systems show qualitatively similar responses, where at high temperatures they're in the susceptibility here, you can see they're polyparamagnets, kind of just a temperature-independent susceptibility term. And then as you cool below a critical temperature, which again is near 100 Kelvin, it varies from system to system. But as you cool below that critical temperature, you see just this dip in the density of states, and indicative of a partial gapping of the Fermi surface, consistent with the onset of charge density wave order. And indeed, these systems do show charge density wave order, and if you solve what the structure of that charge density wave order is, it can be described as basically a breathing mode, or basically a so-called 3Q distortion. So there's 3 different propagation wave vectors for the lattice distortion when one thinks about how the Kagome lattice distorts. There's a breathing mode of the Kagome lattice either into a so-called Star of David pattern, which looks like this, or into a so-called trihexagonal pattern, which looks like this. So these hexagons and triangles, okay? And so the distortions that are in general energetically favored in these systems are for each Kagome plane to breathe into one distortion type or the other, and then and then the differences are in how they sort of stack along the c-axis. So it's a 3-dimensional charge density wave phase, but they can phase, slide like half a unit cell relative to each other along the c-axis, or they can, for instance, modulate the distortion type along the c-axis. And so, this is some details, but indeed this is sort of like they all form 3-dimensional charge density wave states. Okay. So these systems have been of interest because they're sort of, from the community using different probes, they're sort of cumulative signs of broken time reversal symmetry that appear somewhere in the charge density wave state. And can't go through all the experimental results, that kind of show you this. I'll just kind of give you a quick overview, right? So there's experiments looking at muon spin relaxation. For those of you who are familiar with that, that's basically you take a muon and you send it into a material. It's kind of like a tiny, it's a dipole. So basically, you'll see any local magnetic fields, and it'll decohere if there's sort of random fields fluctuating around it, or if there's some coherent field, then they'll all sort of like they'll oscillate as a decay process. And so mu-SR measurements claim that there's some sort of onset of a local field below the charge density, within the charge density wave phase. Magnetotransport measurements seem to, in various regimes, seem to suggest that there are terms that turn on which break time reversal symmetry. There's sort of optical measurements, for instance, Kerr rotation measurements that suggest that time reversal symmetry is broken in the charge density wave phase, as well as sort of like toric measurements, and there's a few others. The issue is that there's sort of controversies that exist in the interpretation of a lot of these, as well as the reproducibility of some of these effects. So it's sort of not settled. People are still studying this actively, but I'll highlight one thing, and I think Vidya is going to talk about this later during her talk, is that a recent result is one of the signatures of time reversal symmetry being broken in the charge density wave phase was originally reported by STM results by Zahida-san's group. And the idea is that you can look at the surface of your crystal, and then when it enters the charge density wave phase, you see some superlattice in the local density of states that forms, okay? And so what the STM people do is they can Fourier transform their surface, and they effectively see these sort of charged superlattice peaks associated with the charge density wave order, okay? So this is in the plane, so these peaks that I've circled here correspond to these sort of 2x2 enlargement of the real space unit cell. And so I think the original idea is that if you look at the Fourier weight associated with these three inequivalent endpoint peaks, then they're inequivalent weights, okay? And so you can ascribe some type of winding that goes from the highest weight to the lowest weight, okay? Which in itself is maybe not super interesting, except to say that there's some chirality at the surface. But the oddity is that if you apply an out-of-plane magnetic field, you can switch the winding of the weights of these peaks, which in a very basic way, very basic level, means that the charge density wave state is somehow coupling to an external magnetic field, okay, which would imply that time reversal symmetry is broken. And so what Vidya's result here is basically sort of reproducing, first of all, that original result by Hassan's, showing that you can actually flip this winding with a magnetic field, but then she also further showed is that you can also flip the winding with a linearly polarized light pulse. And I'll let her talk about it, but it can be mapped sort of an intrinsic piezomagnetic response in the charge density wave phase, which again would imply breaking of time reversal symmetry. Okay, but as one outcome that's come from Vidya's work and many others, also by Philip Mull, is that so the intrinsic features of this system are highly impacted by strain. And these systems are really kind of delicate foils, so people are still trying to figure out how to harmonize the literature by accounting for a strain. Okay, and so if time reversal symmetry is broken, the idea is that perhaps it maps to one of these sort of models of loop current order, or this idea of orbital antiferromagnetism that I discussed yesterday. Okay, so here's a second example. So this is again these sort of 166 compounds, but we're using, instead of manganese, like I described earlier, putting vanadium on that site. So we're changing the filling. And I already described the lattice type to you. Basically, again, it's this bilayer system, and you have an interstitial layer of rare earth ions. And because this Kagome net is now comprised of vanadium, the vanadium-vanadium distance is still close enough that basically there's no local moment on the vanadium site. So it's still ostensibly a non-magnetic Kagome plane that you can interface now with a magnetic or non-magnetic layer of lanthanide ions. And so focusing on the non-magnetic variant, so this is yttrium vanadium 6 tin 6. This is the band structure, and again, you can see for these 166 compounds with vanadium, the Van Hove points are right near the Fermi level. Okay, and so then you can interface these sort of Kagome states near Van Hove filling with variety of different types of magnetic order. It can either be non-magnetic in the yttrium case, or you can interface it with strong uniaxial ferromagnetism by putting in terbium. You can interface it with incommensurate multi-Q order with gadolinium, or easy plane, for instance, by putting in erbium or thulium. Playing these typical games by tuning anisotropies, by tuning the content of the rare earth ions. But for this, I just want to focus on the yttrium for now and just say, okay, the oddity of the yttrium thing is that, okay, you would think that this should somehow map to the physics of the 135 systems, but actually nothing, this system doesn't show any type of phase transitions or order that we've seen, or anything anomalous. Okay. Sorry. But one thing that came out of that is that people started playing around with these systems, and they tried looking at different non-magnetic variants. And one thing you can do is you can replace yttrium with a much smaller ion, scandium. And so this is something that David Mandris's group did. And when you do that, and you look at the susceptibility and resistivity and heat capacity, a phase transition indeed comes about. Okay? And so the question is, does this phase transition have anything to do with, does it map to any of the physics in the 135 systems I showed you? Okay? So it turns out what the unit cell does, this is the bilayer unit cell, as you go through this transition, there's a charge order transition, and it enlarges in the plane root 3 by root 3, so it's a sort of the Q vector is a third, so it's a K point type of distortion, but then it enlarges by 3 times out of the plane, so you have a really big unit cell in the charge ordered state. Okay, I'm sorry. So this is a different K vector from the 135 systems, but nevertheless, one wants to try and understand what's going on in this charge-ordered state and whether or not it can be mapped to some bigger, more generic picture. And so what it turns out is in these compounds, if you look at DFT, so this is just looking at the energy of stable structural distortions of the system. This is from Bing-Hai Yan's group. It turns out there's a reasonably shallow energy minimum with a lot of different charge density wave patterns or charge order patterns that are predicted within a fairly close energy spacing of each other. But actually the most energetic, the energetically favored structure is not a root 3 by root 3 by 3 unit cell, but something with sort of a K point in plane distortion, but times 2 along the C axis. Okay? And so I think this sort of oddity led a lot of people to try and understand exactly what's going on into this system. And so one thing that you can look at in this compound is you can look at diffuse scattering. Okay, so you can look at the wave vector associated with this structure, which is not the ground state. Okay, this is the wave vector that DFT predicts should be the ground state. But and what you find is that when you look at diffuse scattering, which corresponds to like short-range charge correlations, you find that there's actually substantial diffuse scattering even at room temperature in this system that grows and increases in intensity until you hit the charge order transition and then starts to diminish. So this is like kind of critical-like scattering, but over extremely large temperature regime, but it's at a different wave vector. And so this is, I've just shown some data from our paper, but actually Santi has done some beautiful work also studying this. And so the question is basically what's going on and what's driving this. And is there anything odd? And so it turns out in this structure type, when you put this tiny atom on this R site, then what you do is basically you promote a trimerization or sort of stronger bonding between the tin, the rare earth site, and the tin above it. Okay, so I'm looking along the C axis. I can imagine I form these little trimers that sort of thread through the Kagome plane. And here's the red balls here are the hexagons in the Kagome plane. Okay, and so what happens is when you try and form one of these trimers, the tin atom tries to push down, kind of back into the center of the Kagome plane, like in the 1-1 structure. But there's some steric penalty if I look down the C-axis. The vanadium ions don't like that, right? So you can imagine sort of in a heuristic model that they kind of want to move away. So that means that you don't want to put this guy in the one hexagon doesn't want to push in the neighboring hexagon as well, okay? So if I think about how I'm going to try and decorate the centers of the hexagons in the Kagome plane, I get a triangular lattice. And if I think about this trimer can either push up or down, then I have like an Ising degree of freedom, and then you can easily see how you can have a sterically frustrated model with sort of like a 2D Ising kind of degree of freedom. And so, and that 2D Ising degree of freedom is this trimer either shifts up or down to try and accommodate and kind of relieve this crystallographic frustration, which is actually mediated via the Kagome net. So this is just an example of an oddity that happens due to an out-of-plane chain instability, but nevertheless, due to the triangular lattice associated with the honeycomb net of the Kagome net lattice, you actually end up with this sort of steric frustration, which is sort of just native to the system. And it has impacts on the electronic properties of the compound, actually. So here's another example. This is FEGE, where similar physics occurs. And so this is a Kagome net of iron, and it's sort of 1-1 structure. And this system has magnetic order. Okay, so you have out-of-plane moments associated with the iron. It's a very complicated mixture between a charge order transition in this system and magnetic order, but the chain-like instability exists in this compound as well. So if you think about, this system undergoes a charge order transition where, again, the primary motion is really these germanium atoms that are moving towards each other or away from each other. And so this is other work by Santi, more recent work, showing basically if you just look at sort of the thermal displacement of the germanium ions, even like at high temperature, you can see that they're sort of fluctuating and wanting to do this. And indeed, he also sees high temperature diffuse scattering, indicative of sort of this sort of frustration of charge order, of this chain-like instability. It's just an example. This is now more of a lattice-based versus electronic-based example of some unusual behavior you can get in these Kagome compounds. Okay. All right, so I want to show another example, and this is now a system which I'll say sort of beyond the band picture. And I say that because you can look at a system like this. So this is now cesium, titanium-3, bismuth-5. So it's still 1, 3, 5. So it's like the material I showed you at the beginning, or not the beginning, like a couple sections ago, where you had, when these were vanadium ions and this was antimony, it was near the Van Hove filling, but now we've replaced vanadium with titanium. You have completely different filling. And in fact, the Fermi level doesn't seem to be close to much of anything. And if, trying to identify Kagome features in here is getting more challenging. But if you look at this system, indeed, like nothing spectacular happens. If you look at sort of susceptibility or resistivity, so the resistivity is a function of temperature. This is for the rubidium, and this is for the cesium compound. It's just sort of a normal metal. If you look at the susceptibility, you can compare it between the vanadium 135 and the titanium 135. You see the charge density wave transition in the vanadium system, and you see there's pretty much nothing in the titanium system. Okay, so it initially appears to be boring metals, but nevertheless, somehow, there's some type of hidden symmetry breaking in these systems, where this is some work by Ilya Zeltovich's group at Boston College, where they're looking at quasi-particle interference patterns, which I'm sure Vidya will explain more in her talk about what the technique does, but it's a way of visualizing the band structure with STM. And they can look at sort of the electronic, the band structure as a function of angle, basically in plane, and they basically see the onset of a rotational symmetry breaking at low temperature, right? So it's basically a twofold anisotropy in a system that should be sixfold rotationally symmetric. And if you look in the average structure of the system, there's certainly no structural phase transition, and the system seems to fit well to a typical hexagonal Kagome lattice. Okay, it's just an example that clearly there's some other stuff going on in some of these systems in terms of correlations that is sort of intrinsic to the Kagome net that's perhaps missed in DFT. And so another example of just moving beyond the stuff I was talking about earlier, there's a substantial body of work looking at Kagome systems that are magnetically ordered, but magnetically ordered in sort of a non-coplanar spin texture, so manganese-3 tin or manganese-3 germanium, and there's other related compounds. And these systems, again, have this very kind of complicated magnetic texture in real space, which then gives you this real space Berry curvature that Alan introduced a bit, which can then also drive at a large anomalous Hall effect. And so these systems show a really large anomalous Hall effect even at room temperature. So this is just an example of Kagome physics that's like moving beyond just band structure, but thinking about, like, for instance, now this is real space spin texture of the types of magnetic order that are stabilized across the Kagome net. Okay. And I think, yeah, okay, good. I'm doing good on time. I'll keep us on track for lunch. This is the last one I want to say. I just want to focus on my personal opinion is that there's actually a fairly large material space for trying to tune this further, and I think people are just now starting to kind of play with it. So, for instance, if one thinks about naively sort of three-dimensional lattice structures, one can think about these sort of either Lave's phase type materials or this sort of manganese copper 2 type systems. You can take these binary intermetallics, which have Kagome net structures, which I showed you at the very beginning that there's really abundant in nature, okay? But many of them are three-dimensional networks. And then by moving into a ternary space, by, for instance, in this case, just for instance, taking one of the sites, in this case, the B site, and splitting it into two, and one's, for instance, just using like size considerations, one's small, the other's large. Then you can then basically cause an ordered alloy to form, and you can basically chop this naively three-dimensional structure into two-dimensional planes of Kagome. Okay, so this is the chemical phase space to try and explore. This is actually pretty vast and reasonably unexplored. And here's a recent example, right? So you can systems of this so-called 132 structure. So tantalum-2 vanadium-3 silicon is a recent example. It's a superconductor, but there's lots of other ones that have been explored in the past. But I think this is a really big space, especially since you're starting with a large compositional space of binaries that already have Kagome networks in them. Okay. And so yeah, so I'll just conclude and I'll just say, all right, I think there's a growing number of materials manifestations of some of the key ideas that are predicted in Kagome metals, ranging from large anomalous Hall effects to potential indications of sort of orbital antiferromagnetism, as well as sort of correlation-induced flat band effects. The material space is big, and a lot of it's highly tunable, which I think we're seeing the results of that coming out, increasingly year over year. And I think, yeah, I think some of the future directions would be of interest would be I think a lot of people are trying to look now to add multiple instabilities within the same materials platform. So for instance, I mentioned FEGE has both charge order and magnetism. So people trying to look for ways to sort of interface these different order parameters in different sort of Kagome systems, or for instance, also adding superconductivity to the mix. And yeah, I think there's fun ways to try and play with the chemistry. And with that, I thank you very much for your attention.
Is the Dirac cone a 3D Dirac cone or a 2D Dirac cone?
I think naively it's 2D.
2D, yeah. So you think of the band structure as being basically quasi 2D, these materials?
Yeah, yeah.
Okay, thanks.
So what happens when you add the third dimension? If you look closely at the band structure, then does it turn into a 3D Dirac point, or?
Yeah, that's a good point.
Maybe there's not one answer.
Yeah, that might depend on the material, but it's a good question. I don't know the answer. Ming. Oh, okay. Okay. So in the extreme example, she said pyrochlores become 3D. ¿No?